Hello, my name is Owen Embury from the University of Reading, and I'm presenting an update on the sea surface temperature climate data record from the ESA Climate Change Initiative. We are currently preparing to release the third version of our climate data record. This will cover 42 years from 1980 to 2021, along with an ongoing interim CDR which extends the dataset within 3 weeks of present. The main improvements over version 2 are the longer record length by including data back to 1980 and immediate availability of the ICDR extension, improvements to the AVHOR processing to reduce data gaps in the 1980s, processing of AVHOR1 instruments, addressing the biases caused by desert dust aerosol, and implementing a new bias-aware optimal estimation retrieval. Additionally, we are now processing METOP AVHOR at full resolution and have added both SLSTR and microwave AMSA instruments to the main climate data record. This slide shows the coverage of the various products. The infrared products are available at all levels from L2P to L3C. They include both the skin retrievals at satellite overpass and a 20 cm depth estimate for 10:30 local time, which is representative of the daily average SST. Due to the lower resolution of the microwave sensors, the AMSA products are only available as level 2P. They include both subskin at satellite overpass and the time-adjusted 20 cm SST. Finally, we also produce a satellite-only SST analysis using the Met Office Austere system. The dual-view ATSR and SLSTR sensors allow a very accurate coefficient-based retrieval, fully independent from in situ, through the use of physically based radiative transfer modelling. In the case of the ATSRs, we have kept the previous version 2.1 files unmodified, as they were already very stable and showed excellent agreement with in situ validation, as shown in the plots here. For the SLSTR sensors, we use the same Bayesian cloud detection and coefficient-based retrieval as the ATSRs. However, we do need to allow for the more complex viewing geometry and wider asymmetric swath as illustrated on the right here. The SLSTR instrument has a 500 meter resolution for the reflectance bands and 1 kilometer in the thermal infrared. These are observed in a conical scanning pattern with a nadir scan between 0 and 60 degrees and a backward oblique view at 55 degrees. However, the level 1B products are presented on a regular grid aligned with a sub-satellite track, which means that the centre of the observation may be up to half a pixel from its nominal location in the grid. This nature of the level 1B products means we cannot use a simple 2x2 averaging to match the visible bands to the infrared, as shown in this coastal example here. The centre panel shows an SLSTR visible band at 1 kilometer using simple 2x2 averaging, whilst the right image shows the corresponding brightness temperatures in the 11 micron band. In the thermal band, the mismatch between the conical scan and nominal grid has resulted in a sawtooth artifact along the coast. While the reflectance band is a better match to the nominal grid, the pixels are not in the same locations as the thermal bands, so they are not suitable for cloud clearing the SST product. So we need to regrid the reflectance bands to the actual locations of the 1 kilometer thermal pixels. We do this using a K nearest neighbour algorithm, which can use all the reflectance observations, including orphan pixels and both A and B stripes where available. This is shown in the example on the right, where we see that the reflectance band is now correctly aligned with the thermal, allowing us to use it in combination with the infrared for cloud detection. The overall SLSTR performance is now comparable to the ATSR2 and double ATSR instruments. The regional biases compared to in situ are very uniform, with no noticeable cold dust biases. Global median bias relative to drifters are a couple of centikelvin, and the robust standard deviations fall between ATSR2 and double ATSR at 0.25 Kelvin during the day and 0.19 Kelvin at night. With the single-view AVHOR sensors, we use Bayesian cloud detection combined with a bias-aware optimal estimation retrieval. Basic OE will only give an optimal result if the prior fraud model and measurements are all zero mean bias with well-known error covariance matrices. In practice, this is not the case, so we use bias-aware OE as described in Merchant et al. 2020. This uses a match-up dataset of satellite observations and reference SST to retrieve the biases and error covariance matrices, similar to the bias correction techniques used in data assimilation. For the METOP AVHORs, we can use the dual view sensors as the reference, so their retrieval remains fully independent from in situ. However, the earlier AVHOR instruments do not overlap with the dual view sensors, so for consistency, all the NOAA AVHORs are referenced to in situ measurements. In other updates to the AVHOR processing, we are using a newer version of RTTOV, our previous CCI analysis as the prior SST, and include CAMS aerosol in the prior atmospheric state. One of the known problems in the version 2 AVHOR was the cold biases caused by desert dust aerosols. These biases had a strong seasonal signal up to a Kelvin in the Atlantic Ocean and Arabian Sea. They were due to the retrieval assuming clear sky conditions with no dust present. So in version 3 we have added CAMS aerosol, including the dust component, into the clear sky prior. This is taken from the CAMS reanalysis between 2003 and 2021 and the CAMS climatology at other times. The plots on the right show that the dust biases are greatly reduced in version 3 AVHOR compared to version 2. The original instrument design used for the AVHOR1 instruments only had 4 channels, and it did not include a 12 micron channel, so was not capable of the traditional split window SST retrieval. However, they do have both 3.8 and 11 micron channels, which can be used for nighttime only optimal estimation retrieval. We are processing the AVHOR1 instruments for the first time in the version 3 climate data record, which allows us to add the NOAA's 6, 8 and 10 data from the morning orbit in the 1980s. While these data are quite sparse, NOAA 10 does provide overlap with the NOAA 9 and 11 instruments, and NOAA 6 is the only sensor available before August 1981, allowing us to extend the dataset back to the start of 1980. Additionally, we have managed to reduce some of the data gaps in the 1980s AVHOR2 data. In the previous version 2 dataset, AVHOR was affected by intermittent coverage gaps in the 1980s, as shown in this example here. This was due to files received via Wallops Island being wrongly flagged by the quality control checks. This has been corrected in version 3, so we can now process all the orbits and get complete improved coverage as shown here. Microwave SSTs from the Embury and AMSA 2 instruments were experimental products in version 2, but were not included in the main climate data record. We are now including them in the main CDR with version 3. The retrieval is a 2-step linear regression to in situ data, with quality level 5 data showing similar accuracy to the AVHOR sensors with a standard deviation of around 0.35 Kelvin. The AMSA quality level is determined from the retrieval uncertainty, which in practice means that the QL5 data corresponds to the tropics, with lower quality level being found at higher latitudes. This slide shows the data density for all the single sensor CCI products. Version 3 AVHOR GAC is shown in blue, while the black dashed line shows the equivalent from version 2. We can see that the additional AVHOR1 sensors and recovered orbits has improved GAC coverage through the 1980s and 1990s. The 2 drops in AVHOR GAC coverage after 2007 are due to METOP no longer being processed as a GAC sensor. We can see that the data density from the nighttime only NOAA 6 in 1980 and 81 is very low, less than 1 observation per square kilometre per year. However, this is an improvement on having no data. Meanwhile, at the recent end of the record, processing METOP AVHOR at full resolution has increased data density by an order of magnitude. The final product in the CCI climate data record is the Level 4 analysis. This is produced using a climate configuration of the Met Office Ostia system. This is based entirely on CCI Level 2 and 3 SST products and OSISAF CI's Climate Data Record version 2. It does not ingest any in situ data. The analysis is a daily average SST at 20 cm depth. The plots at the bottom show validation against the reference in situ. As expected with the AVHR updates, we are no longer seeing significant cold biases in the dust regions. We still see some artifacts associated with the AVHR retrievals in the 1980s and early 90s, though these have been greatly reduced from the version 2 product. There is a cool bias in the uptick between 2012 and 2017, corresponding to the gap between the dual view ATSR and SLSTR sensors. In addition to the climate data record produced within ESA CCI, we are also producing an ongoing extension as an interim CDR. This uses the same processing system as the climate data record, but replaces error 5 with error 5T and runs daily at 2 to 3 weeks behind present. The ICDR was originally funded under the Copernicus Climate Change Service for 2022, whilst 2023 onwards is provided under UK funding, with the Earth Observation Climate Information Service responsible for Level 3 and the Marine Climate Advisory Service for Level 4. For ease of use, both the CDR and ICDR will be presented as a single dataset through CEDA and the Open Data Portal. Now that we have the ongoing ICDR product, we can use it to look at the recent ocean warming and compare against some other SST datasets. In addition to the CCI analysis version 3, I'll also show CMC, DOI SST and Ostia reprocessing version 2. All three of these ingest in situ observations, though only DOI SST uses Argo, while the other analyses exclude Argo so it can be used for validation. DOI SST was based on AVHR data up until October 2021 and the failure of METOP-A, after which it starts using VIIRS. Both CMC and Ostia reprocessing use microwave SSTs from remote sensing systems, along with AVHR, ATSR and other infrared sensors. Note that while the Ostia reprocessing does use version 2 CCI products for AVHR, ATSR and SLSTR, it is not the same as the version 2 CCI analysis product, which was a satellite-only analysis. The Ostia reprocessing additionally uses the remote sensing system's microwave products and OSISAF geostationary products. These plots show the global mean sea surface temperature from each of the four products, with this year in green, last year in orange and 2021 in blue. In all cases, the global mean SST this year is the highest recorded, about 0.3 degrees above the previous records. However, there are differences. The start of the current record-breaking period ranges from mid-March in DOI SST through to mid-May in Ostia. Furthermore, DOI SST shows the temperatures at the end of March at 22.1 degrees, about 0.2 degrees warmer than the previous DOI SST record. However, in the other three datasets, the end of March temperature was at or below 21 degrees and comparable to temperatures seen in 2016 and 2020. Also, when we look at the temperatures in the years 2021 and 2022, we see that it is close to the mean plus 2 sigma line in the CCI, Ostia and CMC datasets, while in DOI SST it was already 0.1 to 0.2 degrees above the 2 sigma line. Here we show time series of the differences between the various datasets. At the top is the difference between the CCI analysis and reference in situ dataset. Spikes of 0.1 or 0.2 Kelvin are seen in the 1980s, these disappeared through the 90s, apart from one in 2001 corresponding to a period of poor AVHOR data and the ATSR2 gyro failure. After the introduction of ATSR, we see very good agreement between CCI and the in situ data. The lower panel shows the global mean difference between the three comparison datasets and CCI SST. CMC shows a trend of 0.15 degrees between 1991 and 2000. However, after that, it agrees very closely with CCI, with differences less than a 20th of a degree or so. DOI SST shows a longer term trend, being about 0.1 degrees cooler than CCI in the 1980s and 1990s. It was broadly in agreement with CCI from the late 2000s, but has a step change to 0.1 degrees warmer in late 2020. This is likely why it shows the end of March 2023 temperature higher than the other data sets. The Ostia reprocessing shows a few large spikes of several tenths of a degree in the 1980s. This is due to issues in the version 2 AVHOR data it is using. The agreement between CCI and Ostia, particularly between 1991 and 2012, is unsurprising given that Ostia ingests an earlier version of the CCI level 2 and 3 products. However, the data from 2022 onwards comes from Ostia NRT, which does not use any CCI products. Going back to the recent warming derived from the ESA CCI data, in this plot the shaded areas show each time the global sea surface temperature record for a given time of year has been broken since 2012. Before the current year, the last major record-breaking period was the 2015-2016 El Niño. This had record-breaking sea surface temperatures of about a tenth of a degree between mid-March and June 2015, and then a second period starting in July reaching 0.2 degrees in October and 0.3 degrees at the end of 2015 and into 2016. This year the global sea surface temperature was already 0.2 degrees above the previous record in June and reached 0.3 degrees above the previous record in July. Here we show the ENSO 3.4 index with periods of record-breaking global sea surface temperature shaded in red. In this case, 1980s is shaded as record simply because it is the start of the data set. After this, the longer runs of record-breaking sea surface temperature are associated with El Niños as we would expect, with 1997-98 and 2015-16 being the longest continuous periods. The current El Niño is expected to continue into next year, so we can expect the current record sea surface temperatures to continue too. So, to summarise, the version 3 ESA CCI climate data record will cover 42 years from 1980 to the end of 2021, with an interim CDR extension available 2 to 3 weeks behind present. Compared to version 2, we have added AVHOR1, passive microwave for AMSA, started processing METUP at full resolution, and added SLSTR data. The AVHOR retrievals now use bias-aware optimal estimation, and the cold biases associated with desert dust have been addressed. The combined CDR and ICDR is being prepared for release through the CCI Open Data Portal later this year. There will also be a service to allow download of regional subsets and lower resolution products.